Let's tackle part C of problem 63. It's asking us to describe the hybridization around essential atoms as well as to identify the sigma and pi bonds. Now first I'll show you the quick way to answer this type of problem if you were to see it on the test, and then I'll go into a little more detail and elaborate. Now, the first thing we want to know is the bond angles, and that will tell us the hybridization quickly. All right, and this comes from our valence shell electron pair repulsion theory, also known as VSEPR. So in order to do that, we need to draw the Lewis structure, which is pretty much drawn. It looks like that. I'm going to expand it out just a little bit so we can see the H and C carbon-hydrogen bonds a little clearer. So according to VSEPR, and you look at the central atom right here, that's carbon on the left, you want to count how many regions of electron density there are. Well, what do you think? So this is also known as the steric number, and it's 2. There's a region of electron density on either side. So when you have 2 regions of electron density surrounding a central atom, that bond angle is 180 degrees. And if you go to the carbon next to it, you can see it's also symmetrical and also has 2 regions of electron density. Therefore, that bond angle is also 180 degrees. So now that we know the bond angles around the central atoms, we can apply our, if you want to call it a cheat sheet, I'll do that right off here to the side. This is how you quickly answer these kind of questions. When you need tetrahedral or 109.5 degree bond angles around the central atom, you're going to need sp3 hybridization. If you need trigonal planar, in other words 120 degree bond angles around the central atom, you're going to need sp2 hybridization, and that's because sp2s will give you 3 equivalent bonds. sp3 hybridization will give you 4 equivalent bonds, which is what you need for tetrahedral. And then finally, when you need a linear, in other words 180 degree bond angles, which is what we have, you need to mix 2 atomic orbitals and therefore get 2 sp hybridized orbitals. So here's kind of your cheat sheet for all these kind of problems, at least the ones you'll see on our test. All right, so here is your answer. Because we need 180 degree bond angles, this here is sp hybridized, and that here is also sp hybridized. Now, a quick way to answer the sigma pi and the pi question, which is what it's asking us in part 2. Every single bond is a sigma bond. So the CH, the single bond connecting the carbon-hydrogen, that's a sigma bond. That's a sigma bond. And every bond, first bond in a multiple bond is also a sigma bond. So we'll say that bond right there in the middle is a sigma bond. Now, your double and triple bonds are your pi bonds. So that, I'll do a slightly different shade. That one up there, that one down there, those are your pi bonds. All right, so recap, every single bond is a sigma bond, and the first bond in every multiple bond is a sigma bond, and then your second or your third will be your pi bonds. That's your quick way to answer these kind of problems. Now let me go into the explanation to why we need all of this theory to make this acetylene molecule to explain it. So in the case of, all right, well here is the valence electron configuration for a carbon atom. Okay, so there it is. This is carbon, which has 6 total electrons and 4 valence electrons. Now, in order to make a molecule, right, so here's carbon. We know it's because of VSEPR, we know let's just focus on the carbon on the left, right? So there's something here, it doesn't matter, and there's something there, it doesn't really matter. It happens to be H in our problem on the left, there's no left or right spot on one side, and then carbon on the other side, okay? But the focus here is this central carbon. In order to have two regions of electron density, you can't get that 180 degrees. You can't get this 180 degrees of separation using any combinations of S's and P's, because S's, they're just spheres, they're just balls, and then your P's are orientated along the z-axis, the x-axis, and the y-axis. X, Y, Z. They're all 90 degrees apart from each other. This coming right at you, in and out of the screen. Right, and so you can't, this is 90 degrees, and that's 90, they're all 90 degrees. So there's no way you can arrange a combination of these and get two orbitals that are 180 degrees apart from each other. So you'll have to mix two of these. Now, first thing you do is you need to promote this guy up here. Right. So let's when we do that, then we get, let me put this. When we do that, we get now we can have four bonds, because according to valence bond theory, you need an unpaired electron. Like this guy can't participate in a bond because it doesn't have an unpaired electron. So according to valence bond theory, you need an unpaired electron to overlap with another unpaired electron in some other atom's orbital to make that covalent bond. Right, so that's why we promote this, and we can do that because their energies are very similar. Okay, so now since we want two equivalent orbitals, what we can do is mix one of the S's and one of the P's, and these are going to lead to your hybrid S and hybrid sp orbitals. Right, so these are your two sp orbitals, and then these are going to remain unhybridized. They're just going to be your regular px and py. This is your pz, by the way, because that's going to be involved in the sigma bond. All right, so here's what it looks like. Okay, so here's our new hybridized carbon. It has undergone mixing of one of the valence s electron and one of the electrons in the 2pz orbital. Again, now we have two equivalent hybrid orbitals. Now we can separate these guys 180 degrees from each other. So let me show you what that might look like. So an sp and s looks like the sphere I just drew above it, but an sp looks like one of the spheres as well as one of the, remember these are wave functions, so they're not like these discrete shapes, but you'll get something like that. There's your sp. Okay, that's what it might look like. So now that we have two of these guys, we can put one along the carbon, around the carbon, and then I'll put the other one a little bit darker, and there. So there's carbon, there's a carbon on the left, and then the carbon on the right is also going to undergo the same hybridization, because recall up here it also needed 180 degree bond angles. So that one is also going to undergo, what happened? Oh, also sp hybridization. So there's one of the sps, and here's the other sp hybrid orbitals. So each of the carbons have 2 of these sp orbitals, and because they're identical, we can put them 180 degrees from each other. So what kind of bond did I just illustrate? Hopefully you said this is a sigma bond because it's the head-to-head, or the shared electrons are directly on the axis between the 2 nuclei. So there's your sigma bond. All right, now I'm going to draw these electrons in. Okay, so I'm going to draw one of those guys from each of the carbons. All right, so there's my 1 electron from there. There's my 1 electron from there. Actually, I'll put them in this shared region. All right, now the hydrogen, let me just fill that in. The hydrogen on either terminal is bringing in 1 electron in its 1s orbital. Now I'm going to use up the other electron, this one now, from the other sp hybrid. Let me see which color. All right, so there's that. There's that. And so what kind of bonds are these? I hope you said they're sigma bonds as well, because they're also head-to-head. Those shared electrons are right on the axis between the 2 nuclei of the sharing atom. So those are also sigma bonds. Right, so do you see so far what I've drawn is a carbon, single bonded to the carbon, single bonded to the hydrogen, single bonded to the hydrogen. Now we need to draw the 2 pi bonds, and those come from the side-to-side overlap of the unhybridized p orbitals. Right, and that's why we needed these to be x and y, because the z goes in the head-on direction of the axis. This one was involved in the sigma bond that we just made. All right, so now we have the x. I'll just draw this arbitrarily. Let's say this is the x direction. All right, so the px from this carbon and the px from that carbon are now involved in side-to-side overlap. All right, so this way. This region is where you're going to find a pair of electrons. So this is 1 pi bond right here. That's a pi bond, and that whole region above and below the nucleus, the axis separating the nucleus. Right, so you're going to find 1 electron there somewhere, and 1 electron there somewhere. Now, the other p orbital that's unhybridized, that was never touched, is going to be your py. Right, so that's your py, and that's your py. One from each of the, sorry, I keep drawing z's. All right, so now they're 90 degrees. They're 90 degrees from the other p, and they're also 90 degrees from the z that was hybridized in the sp. All right, this is not the easiest thing to draw. It's 3-dimensional, but they're not all 90 degrees away from each other, and so there's that region between those py's, and there's going to be an electron in there somewhere. There's going to be an electron there somewhere, and that is going to form your 2 pi bonds. There's one there, and there's one there. Pi bonds. So hopefully that helped a little bit. I know it's not the easiest topic, but the best thing I can say is just practice and see if you can recreate this from scratch so it runs through visually in your mind. Good luck.